Hello.
Hey, Scott, if you can go ahead and mute yourself and turn your video off, we're not quite getting started yet, just so you know. That's okay. Hey, everybody, and welcome to the 13th Astronomy on Tap Charlottesville. As usual, I am Matt Pryal, aka Dr. Buzzed Lightyear, and I'm going to be your MC for tonight's event. So cheers to everyone. Thank you for joining us on this, if you're in Charlottesville, this beautiful summer day. But it's great to be able to have a lot of fun astronomy on tap, astronomy talks and trivia that we have planned for you. And we have a great set of speakers tonight. And so yeah, as usual, I'm just going to introduce Astronomy on Tap. And I want to encourage everyone this event to try to make this as interactive as possible. If you have any thoughts, you have any questions, don't forget we have the chat window open. All of the panelists have access to the chat. And so I highly recommend you guys chatting with us so I'm not just talking to a blank wall the entire time. Tonight's speakers are Kristina Nyland, Pablo Carrillo, and Bri Mills, and Ed Murphy is going to be doing a segment for us about halfway through the event. And I'm going to be emceeing it the entire night. So let's go ahead. And so for those of you guys that don't know what Astronomy on Tap is, or Astronomy on Tap Charlottesville, we founded Astronomy on Tap Charlottesville in the UVA, or the Charlottesville community, in October of 28. It was started by graduate students. And the whole idea is just to bring astronomy to the Charlottesville community in a fun and relaxed setting. And now that we've been able to do things virtually, we've been able to open up our Charlottesville family to people all over the world. And so it's great to be able to have speakers, not just in Charlottesville. Maybe they're connected to Charlottesville, maybe not. But we've been able to have really great speakers from all different locations and people tuning in from all different locations, which is great. Our schedule for tonight's event is starting with the welcome, and then Kristina Nyland is going to be giving a talk on newborn jets in distant galaxies. Then we're going to go into some trivia. We're going to be doing something a little bit new with the trivia today, and that we're going to be breaking the main trivia game into 2 segments. And then we're going to hopefully be able to reveal the winners of the trivia at the end of the event because we have some extra time because of that. So that should be pretty fun. Then Pablo Carrillo is going to be joining us all the way from Chile. He's going to be talking about ALMA and return to operations for ALMA. And then we're going to finish up the rest of the trivia. Ed Murphy is going to be talking about astronomy in the news, or what's up in the night sky, a combo of the two. And then Bri Mills is going to be wrapping up the night with black holes, the cosmic donut makers, already making me very hungry. And then we're going to do some prizes and say goodbye to everyone. And so there actually is, I guess I should maybe point this out, there's a chance this might be my last time emceeing an Astronomy on Tap Charlottesville event. There's a chance I'll still be in Charlottesville next year. My future is a little bit up in the air right now, and so I hope to be able to see some of you guys in person. But if not, Astronomy on Tap Charlottesville has been awesome to MC it. There's a chance I might be able to join you guys still in the future, so who knows. But yeah, so here are our talks, the posters that we've posted on the social media. We have, if you haven't seen these, but you've found out about Astronomy on Tap Charlottesville through other means, check us out on Facebook. We also have a Twitter. That's usually where a lot of our information is being passed around to. Today, as usual, we like to collect donations for different organizations in the Charlottesville community. And so Catherine has gone ahead and linked where we're going to be raising donations for tonight. And it is for the McCormick Observatory, the observatory in the Charlottesville community that's been home to many different observing events, star parties, the museum, a lot of great educational opportunities, all the way since 1885. And so the donations help the observatory continue doing what it's doing. And additionally, really exciting news, there's going to be 2 donors that are matching all donations tonight to McCormick for up to $250. So we can raise quite a lot of money to help out McCormick in something that we all love, astronomy, right? And so if you're able to donate anything, please donate at the link that's attached here. I see To Infinity and Beyond buzzed. Yes, absolutely, for sure. All right, and so I always forget to do this, and so I've decided to actually put it in the slides today to remind people to use this Q&A feature. During the talks, you can ask questions via the chat and the Q&A. We'd recommend the Q&A to make it a little bit easier on us. But you go ahead and click the Q&A, ask a question at any point during someone's talk, and we'll go ahead and ask that speaker at the end of their presentation. And so as usual, we like to get to know who is watching with us tonight. And the first question I have to you is, where are you watching from? This is our where we had people watching from last time. Majority of people from Charlottesville, but we still had some people tuning in from outside of the US. So Catherine should go ahead and make that poll available to you guys. And go ahead and answer that question. I am still watching from the Charlottesville community. Uh-oh, it looks like hosts and panelists can't vote. That's okay. You guys know I'm watching from Charlottesville. And it's more important to see where everyone else is tuning in from. And don't forget you can share in the chat where you're watching from if it's elsewhere in Virginia or outside of the US, for example. I might have some of my students tuning in tonight. Watching their professor dress up like a Buzz Lightyear is probably very interesting for them. But that's okay. All right, so we can probably go ahead and show those results. Oh, wow. So it looks like the majority of the people watching today is outside of Virginia. We got a couple of people tuning in from outside of the US as well. That's awesome. I'd love to see where some of the people are attending from. If you want to go ahead and share that in the chat, that would be cool. Hopefully we have some people tuning in from Chile potentially to see Pablo's talk. North Haven, Connecticut. Awesome. See you there, Fred. Watching from Afton, Virginia. Nice. Westland, Michigan. Halfway between Detroit and Ann Arbor. Oh, nice. And Mesa, Arizona. Wow, we're all over the place. Louisville, Kentucky. I love it. It's a shame. When we go to potentially back to in-person events, hopefully we can still keep some virtual component so that we don't lose that virtual Astronomy on Tap Charlottesville family. And then flew on the Big Island, Hawaii Island. Very cool. Fort Myers, Florida. Nice. And Nazareth, PA. Back home in the area where I am. I'm from Pennsylvania as well, northeastern PA. Good to see some family tuning in. All right, let's go ahead and make the next question live. What are you guys drinking tonight? So I'm drinking some wine tonight. This is actually wine that was given to me after my sister had a wedding reception over the past weekend, and I was able to leave with the extra wine that we have. And so I'm drinking some of that wine from my sister's wedding reception. So thank you, Bridget. Shout out to Bridget for getting married. All right, so what are you guys drinking tonight? Looks like I actually can answer this question. Nice. This is Astronomy on Tap, Charlottesville, after all, but that doesn't mean you necessarily have to have an alcoholic drink if you're drinking some coffee, tea, soda, or something else. So why don't we go ahead and show those results, Catherine? Got majority of people drinking water and beer, it looks like. 29% water and beer, got some wine, we got some liquor. I was considering getting a margarita over at Guadalajara, but decided against it. I instead went and got Wayside Chicken instead in Charlottesville. And then we got a good amount of people drinking coffee and tea. Very nice. All right, third question up. We got 2 more questions to go before astronomy talks get going. What is your astronomy experience? We want to be able to reach as many people as we possibly can, not just experts in astronomy. And so that's the whole goal with Astronomy on Tap Charlottesville. Although at this point, I can no longer click that I'm an astronomy student. It's been the case for 6 months, even if I like to think it's not, or it is, or it's not. I am no longer an astronomy student. I am Dr. Buzzed Lightyear, after all. All right, so why don't we go ahead and make that a lot of fans. We got a lot of fans and one with no experience. I love it. People that don't have any experience, those are the type of people who are trying to drive into getting excited about astronomy. A good amount of professionals, astronomy students, and amateurs. So thank you guys all for tuning in, for sure. Then we always like to end it with a fun question. The fun question for tonight, not that any of the other questions weren't fun, but what is your favorite astronomy-themed candy or snack? I tried to put as many as I can think of here, but if the answer is other, please share in the chat what your other most favorite candy is. I know my dad's favorite candy, I think, is frozen Milky Ways. Maybe you can confirm that in the chat or not. Mine is certainly just generally Milky Ways. Love Milky Way. Is probably my favorite candy bar in general, astronomy themed or otherwise. Quasar Bars. I've never heard of Quasar Bars. So Kristina, one of our speakers, says Quasar Bars from Trader Joe's are their best. Red vine, licorice, moon cakes, nice. Never heard of a moon cake, I think. Is that different than a moon pie? My Aunt Joan saying Milky Ways. Nice, Aunt Joan. All right, so we can go ahead and show those results, Catherine. Everyone's saying Milky Ways. Let's go. Yes, Milky Ways, absolutely. Believe it or not, the Milky Way candy bar was actually named after the galaxy. It is not the other way around. Milky Ways are a little bit younger than the Milky Way galaxy by a couple billion years or so. All right, so what we're going to be doing now is we are going to be transitioning to our first talk of the night. And so our first talk is by Dr. Kristina Nyland. And so Dr. Kristina Nyland is a National Research Council postdoctoral fellow in residence at the U.S. Naval Research Lab in Washington, D.C., where she studies galaxies, supermassive black holes using radio telescopes from around the world. She's especially interested in understanding how feedback driven by radio emitting jets influences galaxy evolution. She obtained her PhD in 2015 from New Mexico Tech and has previously held postdoc positions in Astron in the Netherlands for radio astronomy and also at the NRAO here in Charlottesville, Virginia. Today, she is going to be talking to us about newborn jets in distant galaxies. So go ahead, take it away, Kristina.
All right, thank you so much for the introduction. All right, looks like I can share. While I'm getting my screen set up, I'll just reemphasize that I do have a connection to Charlottesville. I lived and worked there at the National Radio Astronomy Observatory from 2015 to 2018. And so I am very excited to talk to you today about my research, and maybe I could even come back at some point down the line in person to tell you even more. All right, so I'm going to assume everything is sharing okay and get started. So this evening, I'm going to be telling you about actively feasting supermassive black holes that were recently discovered to have launched newborn jets of radioplasma in the past 10 to 20 years. So I'll start off by introducing you to supermassive black holes and their jets, and then I'll share with you how we observe and study them and why they are important for understanding our cosmic origins. And if I have time, I'll also talk about how supermassive black hole jets impact our everyday lives. So first of all, what is a black hole? So black holes are points in space where gravity is so strong that not even light can escape. And there are different types of black holes. And in this talk, I'll be focusing on supermassive black holes. These are the largest and most massive type of black holes. And they weigh anywhere from millions to billions of times the mass of our sun. And we believe that supermassive black holes live in the hearts of most galaxies. And that includes our own galaxy, the Milky Way. So our supermassive black hole in the Milky Way, it weighs about 4 million times the mass of the sun. And this is an image of the night sky taken from inside the Milky Way on the Earth. And you can see this hazy band of light here. This is the center of our galaxy. And it's near a constellation called Sagittarius. And Sagittarius makes sort of a teapot shape that points right to the heart of our galaxy, where the supermassive black hole lives. Now, if we could see our galaxy from the outside, it would look something like the schematic diagram that I've shown here. So the Milky Way is a barred spiral galaxy, and it measures about 100,000 light years across. And I have a little arrow here pointing to the location of our solar system. We're about halfway between the center of the galaxy and the outskirts. So we are around 25,000 light years away from our supermassive black hole. Now, supermassive black holes, by their very nature, they don't emit any light. Their gravity is too strong. Light cannot escape. But we can detect and study them indirectly by observing radiation that's produced by material that heats up as it feeds the black hole. And so this is a picture of the center of our galaxy taken with an X-ray telescope. And the whole central region of our galaxy is very hot and hostile. But I just want to highlight this little zoom in box here, this little blue blob, that is actually the location of our supermassive black hole. Now, another way of studying supermassive black holes is by observing the effects of their gravitational fields on nearby stars. So what you're seeing here is a video of real data taken tracking the orbits of stars around our galaxy's supermassive black hole. And this took decades to compile. And this effort was recently recognized internationally. The Nobel Prize in Physics in 2020 was awarded for supermassive black hole research. Now, the Milky Way's supermassive black hole is interesting because it's so nearby. But when you compare it to other galaxies, it's actually pretty wimpy. And that's because it's feeding at an extremely low rate. It is the most underfed supermassive black hole that we know of, that we're able to detect. And so this is a comparison of the Milky Way, shown here on the right, with another galaxy, an elliptical galaxy called Hercules A, that is 1,000 times larger than the Milky Way. And its supermassive black hole weighs around 1 billion times the mass of the sun. You'll also notice that unlike the Milky Way, Hercules A has these beautiful plumes of radioplasma traced by this pink emission. These are, we call these radio jets or lobes when they sort of disperse after they've traveled a long distance. Now, through physics that we're still working on understanding, about 1 to 10% of actively feeding supermassive black holes are able to launch powerful radio jets along their magnetic poles like these. Now, even though we're still working on understanding the physics of how jets are formed, we do know that they shine via a process called synchrotron radiation. So synchrotron radiation is electrons that are spiraling around magnetic field lines that get accelerated up to nearly the speed of light. And this is a little diagram showing that. Now, over millions of years of time, radio jets can reach these large spatial scales. So this is 1.5 million light years wide. Remember that our galaxy is only 100,000 light years wide. So radio jets can really have a big impact over the area surrounding their galaxies. And in fact, they release tremendous amounts of energy into their environments. And all this energy creates turmoil in the gas supply of a galaxy that would be used to form new stars. And this ultimately causes the stellar birth rate to sharply decline. And so supermassive black hole jets influence the future life and appearance of galaxies. So supermassive black holes play a really important role in shaping the growth of galaxies over billions of years of cosmic history. So in the diagram here, this is a schematic showing the history of the universe from the Big Bang on the left to this point in time here, about 1 billion years after the Big Bang, when the first galaxies formed, and then on to the present day, 13.8 billion years later. Now, let's see. We've been studying radio jets and how they influence galaxies for a long time, and we have a pretty good understanding how the most extreme, largest scale radio jets and lobes affect the fates and futures of galaxies. So we have a pretty good handle on that. What we don't really understand is how jets affect their surroundings when they're young and still confined inside of their galaxies. That's remained pretty elusive, even though we've been studying radio jets for decades now. So the real question that I'm interested in my research is, how do young jets influence galaxies? And before I tell you about some new research I've done in that area, just want to briefly mention something about how we actually study jets. I want to share with you some of the tools that I use in my research. So what you're seeing here is a video clip of a professional flyover of the Very Large Array, or the VLA for short. Now, the VLA is a radio telescope. So it takes pictures of the sky at radio wavelengths, and it is the perfect tool for studying radio jets. So just a little bit more about the VLA. It is one of the world's premier radio telescopes, and it consists of 27 individual radio dishes. And these dishes are linked together electronically, and they effectively form a single large telescope. Now, each dish is about 25 meters across, that's around 80 feet. And they're arranged on specialized railroad tracks. And a few times a year, a very specialized vehicle picks up each antenna weighing 220 tons and drives it up or down the tracks. And this changes the level of detail and sensitivity of pictures taken with the VLA. So just a few more fun things about the VLA. It is located in New Mexico in the southwestern United States. I have a little marker at its location. If you ever find yourself in central New Mexico, I highly recommend paying a visit to the VLA. You can take a look at there's a public website that you can visit to learn about tours and what kinds of things you can see at the site. Just a couple other fun things before I get back to the science. The VLA has been featured in numerous films and media, the most famous of which is probably the movie Contact, which came out in the late 90s. It is one of my favorite movies. If you haven't seen it, I recommend it. But I always like to point out one little detail. If you have a sharp eye, you might see that Jodie Foster has some headphones around her neck, and she's depicted in the movie as listening to radio signals from the VLA. That's not actually how we do it. We don't listen, we watch the universe. We take pictures. The VLA is a kind of camera. So if you check out the movie, just keep that in mind. And then, of course, I have had the amazing opportunity to actually go inside some of the VLA dishes. That's sort of a perk of being an astronomer, of being a radio astronomer in particular. And so I just couldn't resist putting in a couple pictures of me inside one of the dishes and having some fun as a grad student. Okay, so back to science. The VLA has been around since 1980, but it was recently renovated, essentially, and the electronics were upgraded, and it has become an even more powerful tool for exploring the universe. And one of the ways that telescopes like the VLA are able to really make a big impact on science is by conducting surveys. So these are systematic pictures taken of the entire sky, or usually orchestrated by an observatory. So the VLA is currently embarking on a survey called the Vla Sky Survey, or VLAS. And these are some pictures that were taken by VLAS in the past couple of years. So VLAS is not the first survey that's been done with the VLA. There were a few historical surveys that were done in the 1990s. And so I have a little timeline here comparing VLAS, which started in 2019, but will continue in the next few years. And then in the 1990s, I've highlighted a survey, previous survey called FIRST, Faint Images of the Radio Sky at 20 centimeters. And so this gives a really interesting opportunity to compare the two surveys and try to see if the radio sky has changed over time. And so with the goal of attempting to catch jets as they were being born from known supermassive black holes, I set out to do that recently. And so in I have an animated GIF here that's showing you a comparison of real data between these two surveys. And the objects you're seeing, these are the positions of active supermassive black holes that were found by observations at other wavelengths. So these are supermassive black holes that didn't have any evidence of jets in the 1990s. But when we checked 20 years later, bright sources were present at those locations. So this is really, really exciting. And to make it more exciting, of course, artists, can really paint a more vivid picture. So I have an artist illustration of what's going on here in the upper right. So in the 1990s, the objects we were targeting, these were galaxies that had active supermassive black holes, but no jets. And then 20 years later, you can see the artist depiction of a young jet being launched. And one other thing to highlight, the galaxies where these supermassive black holes live, they are very distant. They are from a period of the universe when galaxies were sort of in their most actively forming and growing state, about half of the universe's current age. So these galaxies are, the light started traveling towards us about 6 billion years ago. And so it's really kind of mind-boggling to think about, we're seeing these distant supermassive black hole jets being born on human timescales. And I sort of had fun reminiscing while I was putting together this talk, thinking about what was going on in the 90s, what was I thinking about, and then how things have sort of changed. All right, so in the last segment of this talk, I want to share with you why this is important. And there are lots of reasons. I'm going to try to just focus on two. So supermassive black hole jets are important for understanding galaxy evolution and then also for celestial navigation. If you remember when I was introduced, my institution is, I have a postdoc position in residence at the US Naval Research Laboratory. And so I'll try to very briefly, not go too much over in time, tell you why jets are important to the Navy. So for all the details, please visit the paper. And if you're an astronomer, please check on this nice long list of co-authors who contributed to this work. I'm talking about it like I did it, but I really had a really fantastic network collaborating with me. So going back to this cosmic history slide, one thing that we found is that there are more small and young jets than we thought there would be. And this suggests that jets may commonly be triggered, but they don't live for a long time. So frequently triggered, but short-lived jets are more common than we thought. And that has really important implications if you want to understand how jets have changed the universe over billions of years of history. And it's something that would be important to fold into cosmological models of the universe. So this is really, really exciting. And this is, this is why I did the study in the first place, was to understand this. But it turns out that, changing gears here a little bit, it turns out that supermassive black hole jets also act as cosmic beacons for celestial navigation. And we've actually been using distant supermassive black hole jets for defining an accurate reference frame grid for a couple decades now. And I have a little cartoon illustrating it. So we have the Earth here. We've got satellites flying around the Earth. The Earth is precessing on its axis. We have radio telescopes on the Earth. The plate tectonics are moving the land around. And then we need to tie all of that to a common frame. And supermassive black holes at very large cosmic distances are a great population for that. Quasars, which is another word for an actively feasting supermassive black hole, they act as cosmic beacons. Here's a sky map showing the locations of thousands of supermassive black hole jets that define something called the International Celestial Reference Frame. And so this is what the Navy is really interested in. It's really important for things like spacecraft navigation. And to have and maintain an accurate grid, you need to monitor the positions of jets to make corrections for changes to their fluxes and positions. But we don't really understand how, why, or when changes might happen in the properties of jets. So that's why we really need to understand how jets form and grow. And finally, I just want to mention, if you are interested in learning more about the research that's done at the Naval Research Lab, there is a nice public webpage here with some information. And I will then move on to my summary. So the take-home message that I'll leave you with is that newborn supermassive black hole jets are important both as galaxy influencers and beacons for navigation. And with that, I'm really happy to take any questions that you have, or you can contact me. I have contact information on my website. So thank you.
Awesome. Thank you so much, Kristina. That was an awesome talk. And it was the aesthetics of the talk was just like amazing, actually. So you do a really good job putting aesthetically nice presentations together. But I do have a question in regards to the jets. And that is, and so jets play a role, obviously, in sort of you mentioned setting the fate of like galaxies. I'm curious, I thought I had heard that they might limit how large a galaxy can get. Do jets actually play a role in that? And then like, can you do any information with how large a galaxy can be because of that?
Yeah, so there's this whole symbiotic relationship between supermassive black holes and galaxies that I didn't have time to really get into. So jets influence galaxies, but jets also affect the feeding of the black hole itself. It's sort of like a two-way feedback. So if you have a jet, tunneling through a galaxy, or black holes, supermassive black holes can also emit winds. They might affect the fuel supply also for the black hole, and so there's sort of a co-regulation. We call it supermassive black hole galaxy co-evolution, and we believe that supermassive black holes and galaxies have been affecting one another through feedback mechanisms like jets since the first galaxies formed 500 million years after the Big Bang.
So kind of on that sort of train of thought, is there ways we can find out how a jet might have influenced the Milky Way galaxy in any way? Because would we have more data, because we're in the Milky Way, to be able to test, all the jets that we're observing in the distant universe? If our Milky Way was like this, what should we see, type of thing? Is there anything that you can do with that?
Oh, that's a great question. Yeah, unfortunately, the supermassive black hole in our galaxy, which is also referred to as Sagittarius A star, it just is feeding at such a low rate. It is feeding at a factor of 1 billion below what's known as the Eddington ratio. That's the maximum energy you can get out of an object before breaking laws of physics. That's the most luminous it could be. It's 1 billion times below its full potential. And so it does not have jets. It's possible it might have had more activity in the past. There are some structures called the Fermi bubbles, which are seen in high energy observations, that they're very faint and diffuse, and they do extend like perpendicular to the axis of the disk of the Milky Way, sort of like bubbles going on either side of it. Okay. And yeah, they might have played some minor role, but our galaxy is not the best laboratory for studying how jets impact the lives of galaxies. Yeah.
Cool. So we actually have a lot of questions that just popped in as well, but we might only have time for like 2, and then you can respond to the others via chat, maybe. That'd be great. And so I'll ask, Jeff asks a question: do only supermassive black holes have jets, or do smaller black holes also have jets?
That is a fantastic question. So smaller black holes belong to the population of so-called stellar mass black holes. So when a large star, a much larger star than our own sun dies, sometimes a supermassive black hole is the end result. And they can have jets. I'm not an expert on that specific area. They may not be as fast as supermassive black hole jets, may not be traveling quite as close to the speed of light in some cases, but yes, it does happen. And also jets are they're an even more general phenomenon. There are other types of objects like young stars, for instance, while they're forming, are able to launch jets. So it is kind of a generic process of physics too. But yeah, that's very cool. Supermassive black hole jets are relativistic. They are near the speed of light, is something that distinguishes them.
Right. Oh, and so the stellar jets aren't relativistic?
Well, some of them might be. Also, some supermassive black hole jets could also be sub-relativistic, but the extreme ones that I've been showing.
No, they're awesome. They're relativistic. They're amazing. Black holes are, yeah. All right. Only time for one more question live, and you can respond to the other ones in the chat if possible. But Richard asks, how do we characterize the strength and the size of jets to galaxies? Does it depend on the galaxy's mass, its energy that it's releasing?
That's a very good question. So it sounds like it's getting at what parameters control how powerful a jet is. That is an active area of research, but we believe it is connected to the mass of the black hole, as well as how fast it is spinning, because we think it's sort of like a dynamo effect. The black hole a large black hole has to be sort of spun up to generate powerful magnetic fields, and then electrons get trapped spiraling around those magnetic fields. And it may also depend on the specific feeding habits of a supermassive black hole. Supermassive black hole feeding we use the term accretion. It's not sort of a one-size-fits-all thing. There are different types of accretion, different accretion geometries, different accretion efficiencies. And in some cases, jet production is more likely. So I actually attended a conference all last week on extragalactic jets and heard a lot of debate on this topic. So good question. Hopefully I helped answer it somewhat.
Unfortunately, there are like 20 questions still in the chat, but we don't have time to get through all of them. Kristina will probably hang around to be able to answer those for you guys. But for now, thank you, Kristina. That was an awesome talk. And yeah, if anyone has any questions for her, you can reach out at her website, I think, as well as another way you can contact.
Yep, thank you so much. And I'm happy to answer questions on chat. Okay,
great. So now what we're going to be doing, I'm going to start sharing my screen again. And I'm actually going to ask Scott Doreski, if you are still on. He's going to talk to us about the Charlottesville Astronomical Society. And so you can show your video and unmute yourself, Scott, and talk about the Charlottesville Astronomical Society very quickly. If not, if Scott isn't on, that's okay. What I can do is I can introduce the Charlottesville Astronomical Society to everyone then.
I'm Matt, I'm on.
Oh, okay. Go ahead. Take it away, Scott.
I just can't show my picture. Do I need my?
That's fine.
Okay. Good evening, everybody. Let's start my video. Okay, there we go. What? Good evening, everyone. This is Scott Doreski. I'm the Vice President and Observing Director of the Charlottesville Astronomical Society. It does show right in the screen right now how you can find more information about the CAS. But what I'd like to share with you now is this. As we emerge from our pandemic, our period of isolation, later on, late this summer and this fall, we will likely be resuming club outreach and some really exciting observing programs that have been in the works for a while that we will start. Some of them are new to the club. All of them are going to be quite interesting opportunities to observe at dark sky sites. And new for the first time, I can share with everyone, I'm not going to go into the details now. We are going to have a new type of telescope that we can share with people that is a revolutionary kind of telescope, which will display images in the sky that have never been available to amateur astronomers in the field before or people attending such events. So what I'd like to do for all of you, and I guess you can do this in the chat as well, if any of you listening to my voice right now would be interested in being kept hearing more about these programs and when we're going to be doing them, what I would like you to do is to put your name and contact information in the chat. I will reach out to you at that point, and when you confirm that interest, I will make sure that I get in touch with you and share information about some of these programs. All I can say is this is a very, very exciting time, and I would love to share some of this, we would like to share some of this excitement with you. And that's all I have. Matt, thank you so much. Great program this evening, and thank you very much to everybody who's participating.
Awesome. Thank you so much, Scott. And if anyone has any questions, don't forget to let Scott know in the chat. I see there's some people potentially reaching out to you as well. And so I'll make sure to share those with you too, Scott.
Okay, thank you.
Thank you so much.
Sure.
All right. And so actually one thing that I forgot to do, I had written an awesome joke down during Kristina's talk that I forgot to say. And the joke is as follows. So Kristina let us know that jets could change the universe. And I was going to say, jets can change the universe. I thought they were only just a bad football team. Everyone please laugh in the chat. Thank you very much. All right, let's go ahead and move to trivia. That's what everyone's here for. Scott, you can go ahead and turn your video off. That would be awesome as well. And so we should be sharing a link to the trivia in the chat right now. The way that trivia works in Astronomy on Tap is we have a series of 10 questions that you guys have to fill out a Google Doc for. And we're going to go through 5 of them right now, and then 5 of them after Pablo's talk. And whoever gets the most questions gets some award. We also give some prizes out randomly to people who want that as well. And so go ahead, play along. It's a fun trivia game, and thanks to Jacob White for putting together the trivia as always. Catherine has gone ahead and linked that to everyone. And so I'm going to go through each of the questions right now. You have until the end of, or till the beginning of Bri's talk to get all of your trivia answers in. And so question number 1, summer is officially here. Which of the following is not true for summer in the Northern Hemisphere? Is it that the length of daytime starts getting longer? The time the sun spends above the horizon is longer than in winter. The summer starts on about June 20th every year. The moon has essentially no impact on the summer heat, or these are the days of our lives. Which of the following is not true for summer in the Northern Hemisphere? All right, question number 2. Our orbit around the sun is not a perfect circle, slightly elliptical. The point we are closest to the sun is called perihelion, and the furthest point is called aphelion. When approximately is this location when we're the furthest from the sun? Is it early January, early April, early July, early October, or early morning every morning? Question number 3. Remember, we're only going to go through half of them right now. Summer lasts about a quarter of our trip around the sun. If summer were the same on Jupiter, how many months would it last? Would it be 3 months, 6 months, 12 months, 24 months, or 36 months? And this is actually our Facebook trivia hint for today. If you guys want trivia hints, check us out on Facebook. It's how you can keep up with all of our events as well. And so let's go to question number 4. Oh, thanks for sharing Facebook in the chat, Catherine. Question number 4, it's summer, it's hot, but it could be a lot hotter. What is the hottest planet in the solar system by average surface temperature? Is it Mercury, Venus, Earth, Mars, or planet Hollywood? And the final question for right now, before we go to Pablo's talk, we get more direct sunshine in the summer, and that's what helps increase the temperature. But the sun isn't the hottest type of stellar object or star. Which type below is the hottest? Is it a red dwarf, a brown dwarf, a white dwarf, a black dwarf, or a giant volcano star? Ooh, what's a giant volcano star? All right, so that's gonna wrap up our trivia for right now. We're gonna go through the rest of the 5 questions after Pablo's talk. But I do want to just point out that as a reminder, we are collecting donations today. If you're able to donate to McCormick, that'd be great. And up to $250 in donations are being matched by some generous donors as well. And so now's the time to help out and share with McCormick if you are able to. But with that being said, we're going to actually turn to Pablo Carrillo's talk. And so Pablo is actually joining us all the way from Chile. And so Pablo is a maintenance group supervisor at the ALMA array in Chile. And so ALMA, for those, I'm sure Pablo mentioned this, but it's one of the largest telescopes array in the world. And it's opened the door to many different amazing discoveries in radio astronomy. And so what Pablo does is that he's the supervisor and the team lead for the antenna and correlator maintenance. And he's going to be talking us today about a day in ALMA return to operations. And don't forget, if you have questions, check out the Q&A. And I think Kristina is going to be linking some info about Pablo as well in the chat. So Pablo, you can go ahead and share your screen and take it away. We're really excited for your talk.
Okay, thank you, Matt. Can you hear me properly?
Yep, we can hear you okay.
Yep, great. So I'm trying to share the screen without screwing it up. Let me check. So there you go. So
looks all good on our end.
Great. So you're looking at the big one, right? Yes, that's correct. Yes. Okay. So let's see. Well, that's. I mean, first of all, just thank you, Matt, for inviting me. Thank you, Catherine. Yes, we were working together since a few years ago, long time ago, and yeah, I'm still doing engineering and maintenance in the array. And yeah, my presentation is basically how it looks like at the common day in ALMA from the engineering and technical point of view, specifically during the return to operations. I mean, that phase after having the array basically on a whole year without using it and just power off, and which was quite challenging. So, okay, so I will go, let me see, oops. Can Matt, so can you see the main?
Sorry, so what are you trying to show us
right?
right now? So right now we can just see your slide that says a day in ALMA, return to operations. That's about
right. I'm just trying to. Okay, just give me a minute. Okay, very good. I think I'm just.
There we go. Nice.
Okay, sorry. So my nice small presentation So, okay, this is me. I'm just usually a mountain biker, photographer, sandboarder, and mountaineer. And of course, for doing all these funny things, I need to just take the money from somewhere. And that's why I'm just, which is the better place that I could choose for working is just ALMA Observatory. And as an array maintenance supervisor and engineer, as Matt mentioned before. And yeah, I mean, just I'm being here since the construction of the array, basically more than 10 years ago, arriving for the general coordination and processing of the antennas, arriving from the different vendors. And still here, just doing the technical and engineering part for doing the array operational for science. So this is a quick rough fact sheet about ALMA. Well, it's located in Chile, in the middle of the Andes Mountains. It has 66 radio telescopes. I mean, just recently, Kristina mentioned something about the VLA. And this is quite similar. I mean, the antennas are sort of different, but the principle is basically the same. It's a radio telescope that it can put the antennas farther apart or close together for the astronomers' different purposes. I mean, this is an interesting point that they have a 3 megawatts power consumption, just typically feeds a small town, which is quite challenging. And it's about just 250 people of the workforce that work together. And these different locations, I mean, there is an operations support facility, which is where the residence and the camp is located, about 209 meters above sea level, which is 9,500 feet roughly. And about 19 miles distance up in the mountains is the main array where the antennas are located. And that is a quite high altitude. I mean, just 5,000 meters above sea level. And this is how it looks like in the map, but it's not quite representative. So this is a picture just taken a few days ago when they arrived to the shift. I thought that it will be nice and clear, but no, it's just snowing again. So it's quite challenging. And you can see here in the lower part, the OSF, the Operations Support Facility, and behind those mountains is where the antennas are located. And yeah, so I'm going to show you how the array looks like. Oh, no, it's not that one. So it's this one. So this is a nice picture of the ALMA array at the high side, where the whole 66 antennas on it is the compact array in this case. And a beautiful sunny day in summer, but it will be quite different as I'm going to show you in the next slides to you. So from the, science point of view, this is the perfect day. I mean, just sunny, clean, low humidity, and it's perfect for everyday observations. I mean, radio telescopes can observe basically the 24 hours of the day and night. So it's not a limitation only during the night as optical telescopes. But for technicians and engineers, it's quite different and challenging. So this is how a normal day looks like in, in our common work. This is basically taken from a similar movie, not a similar movie, but a different movie that took VLA. As Kristina mentioned, this is the most known one is Contact, but also was shown, I think, in Terminator movie. So this is how it looks like a normal day for engineers and technicians. So we are just dealing daily about different problems in the correlator, in the observations, doing normal preventive maintenance, and some other funny problems that we need to take care of. And I couldn't find another feeling about how to express to deal with this, this funny fellow that we have here. I don't know if we have seen this ice-age squirrel with his eyelid shaking when see all these problems. So that is the technician engineer looks like when it's facing all these issues. But this is in a normal day. What about when something happens and snowstorms coming or a power shutdown or something like that, to return to operations, you're right. So practically non-issue. I mean, this without any problems because the array is shutdowns is so perfect and marvelous days for the technician and engineer. But of course, we need to deal with the recovery process of the whole array, the 66 antennas in high altitude in the middle of the mountains. So we need to prepare to go to the high side, start recovering the array. First thing, okay, checkpoint is the first thing to do. I mean, there's some colleagues there in the line for checkpoint with safety, and the the paramedic to check our blood pressure and the saturation of our oxygen, put our gears for going up to the high altitude. I mean, it's really cold during winter. Temperatures can reach down to minus 25 degrees Celsius, actually, wind chill, which is quite cold. So this is the first thing. So in the way up, we see a beautiful fellows that are besides the roads. I mean, this is a vicuña. It's a parent of a llama, but more stylish. I mean, he's feeding his baby there. And yeah, we're not just wanted to bother you guys anymore. And still on the way up, there is this beautiful little ones that looks like chinchillas, but indeed they call vizcachas. It's a pretty common animal in the surroundings of the ALMA array. And well, and then we get to the array after a snowstorm, and this is how it looks like. Yeah, it's sort of terrible compared with the previous one, right? So yes, it's full of snow. You can see in the ditches that is quite amount of snow that we have to recover and everything. And also we get to our technical building, which is completely covered with snow and ice. And again, it starts our technician engineer just with his eyelid shaking about what we want to do with this and how we can recover the antennas, the building and the technical rooms inside this building. So the first thing that, of course, we need to do, okay, takes our shovels and start to take the snow out of the building to get access to the equipment that is already stored, the ambulance that is inside the building just in case for security purposes. And yeah, it's quite challenging. And actually, I'm just leading this fantastic group of people that do this when these bad weather events happen. But it's not only with these tools that we'll go there. We have the help of big machinery. I mean, this is a huge snow blower attached to a front loader, which is basically the tool that we use to get access to our normal and light vehicles to get access to the antennas. Other way would be practically impossible. But it takes time. I mean, we are talking about days of recovery of the array and getting to the antennas. And for that, we also use this also good machine, which is a snowcat. You've seen this in the ski resorts, something like that, which is quite similar and allow us to get the most far away antennas when the array is in an extended configuration. I mean, the antennas could be spread out of the plateau in the Andes about 16 kilometers far away. I mean, it's a really huge distance, one antenna from each other, and the only way to get them is with this machine. But of course, sometimes we need just to walk. I mean, there is a few distance that we can reach the antennas, and basically you can see the little astronauts here. It looks like something like in Star Wars, Planet Hot, or even Enceladus or something like that. They are just walking through over the snow just to get the antennas and try to recover them. But when the challenging part and the fun part start is how to recover them and what the problems we face to try to get the antennas back to operation. The first thing is just we need to get access to the dishes, and sometimes it's really complicated because we cannot even access to the pedestal of the receiver cabin when the receiver is. So we need to clear the snow first just to try to recover the antenna. Sometimes the snow and the ice gets accumulated in that hole that you can see at your right, which is the feed shutter on the Cassegrain hole of the big parabola, where the signals gets into the receiver, which is inside the antenna. But sometimes we need to wait some 2 or 3 days for the snow to get melt, or we need to another machine just to remove it with our hands and some tools. Of course, the big machinery is also helping us just to clean the array and get access to with our light vehicles for doing our maintenance, but not also preventive maintenance, also corrective maintenance. Many subsystems fails during this recovery. I don't know, the air conditioning system of the antennas fail, and some mechanical individual parts also fail, and we need to be replaced. But indeed, the antennas were designed to survive these conditions. We have these events, let's say, where different of you guys, we are just now starting the winter season. You are happy with the warm seasons at the northern hemisphere, but we are getting the cold season in the southern hemisphere, and we basically have 2 or 3 big snow events to recover the antenna from scratch, basically. And during summertime, in the southern hemisphere, southern time, we also face some snow events that could be very weird, but it's not actually, because it looks like a phenomenon called the antiplanic winter or Bolivian winter that happens during summer. Actually, because of the humidity that is being released for the Amazon, that is accumulated in clouds and finally gets over our antennas during summertime. And yeah, there's plenty of work that we need to do at the high side and individually to get the antennas back to operations. And at this point, yeah, I'm really overwhelmed about the Kristina recent talk, because he basically used these tools, these machines, these beautiful engineering antennas for doing the discoveries. I mean, we basically support all that science that you guys are doing, and that is a very interesting part from our side. Well, this is the presentation, of course, at the beginning was a day in ALMA recovery, and we are getting to the end of the day and just try to recover as much antennas as possible. And at this point, you start to see funny things in the mountain, like this big crocodile. Probably you already distinguished it, that it was something weird with that mountain shape. But anyway, so that's something funny that you can see in the Andes. It's beautiful. And of course, just okay, it's time to go down to the residence and the canteen just to have our meals and resting. But we cannot just go straight. I mean, we have to stop. I mean, there's a beautiful landscape. This is Atacama salt flats. This is a huge, maybe, I don't know, an ancient lake from millions of years ago that got dry, and now it's a salt flat, beautiful landscape. And these are the animals that go down with us. This is a really beautiful Vicuña site at the going down of the after our work, and this is how it looks like the array that we left after 4 or 5 days of full working of recovery. Each individual antenna just to start ready to start again doing science, which is of course our primary goal and for doing what we are doing here. But of course, at the next day of deliver all the antennas to science, guess what? We are doing again, facing the same problems that we were facing before. But come on, it's our work, is what we are here supporting astronomers and science to, as Kristina mentioned, just to discover our cosmic origins. And this is the people that that is really doing ALMA running. I mean, this is the actual engine of ALMA, our people. And that is, I'm very grateful just to work with them and lead them into the maintenance of having this fantastic equipment and tool for you guys, and Kristina, for you for doing your spectacular and overwhelmed science. So thanks everyone, and that's it, man.
All right, thank you so much, Pablo. That was amazing. Were all those pictures were taken by you, right?
Actually, yeah.
That's
yeah,
I mean,
because
that's incredible.
Since I came here, I just enjoy just taking photos everywhere, and I can sometimes I cannot even choose where to put the camera or where to point the camera to. And this is really fantastic place to work.
Yeah, I was gonna say, I don't even know how you get work done. I would just sit and look at all the amazing views and the animals all the time, probably. But yeah, you guys are clearly doing a lot of awesome work. And yeah, I mean, none of this, so just so everyone, the audience knows, as Pablo mentioned, none of the science that's being done with ALMA, all these discoveries that we talk about would not be able to be done with the engineers or the people working on the telescopes. And so all of the majority of the telescopes working is just thanks to those people that are doing that. And so we do have a couple questions in the chat for you. Actually, the first I think a lot of people are probably just generally having this. So you have all this snow that you have to get out of the telescopes at times. What's the reason to even put the telescopes on top of a mountain in Chile if you have to get rid of this snow all the time? If you could answer that for the people that might be asking that question. Why not just put it in, I don't know, somewhere else?
Yeah, that is a really good question, Matt, and I'm just still figuring out why they do that. But okay, no, but even that probably, I don't know, let's say 10 or 20% of the time, the array is really closed or shut down because different problems and mainly weather conditions. Because it's the best flake because of the low humidity. It has almost zero or very, very, very low humidity. And why low humidity is important? Because basically the radio frequencies comes just directly into the ditches. I mean, with very, very low interference with the humidity that's in the air. In the case of the VLA, it doesn't really matter because I understand that the frequency range is different. This is not affect that much the humidity. Even the frequency can go through the clouds and can be received by the VLA dishes. But in case of the ALMA, the frequency range is much higher, and we need a place dry enough to get this signal. That's why they put these antennas here, even that sometimes it's very challenging to recover them.
Right. Yeah. So it is absolutely worth the work for the people that are wondering that question. I have a question from Fred. He's asking, this might have been answered in your talk a bit, but with this much snow and cold weather, is there a problem with snow or ice buildup on the antennas? And so I guess maybe in regards to their longevity, is there might be some effect that they have in regards to how long they can last. You had mentioned that they were built with the intention, of course, for that. But does this affect their life at all?
Well, actually, the ice blocks forms. That's true between the gears, the azimuth drive, the elevation. The antenna moves in elevation and then in azimuth, and effectively the ice is the ice gets accumulated in between. And some stalactite just coming from the antenna is really fun sometimes, but. Yeah, that is a blocker, and but again, I mean, the antennas were designed and built for that purpose, and so far so good. Some antennas are more than 10 or 11, 12 years of age, and we are actually doing some overhaul, 10-year maintenance overhaul of the first antennas that were built, and we haven't found any major problems with about the ceiling or things that could be related from the wet weather. So yeah, they were fulfilling their purpose.
Nice. Okay, great. And then Chris has a question. Basically, I can summarize it more or less as, how is it? So, ALMA's obviously sort of international collaboration at times. And so they're wondering what it's like to work with people basically from from all over the world. I mean, I don't know how much necessarily you're interacting with people that might be using the telescope from all over the world, but maybe the engineers and the people on site. I don't know if you could just talk about what it's like to what the work life is like in
Yeah, right. Actually, it was let's say it's different. It was different in the construction phase, which was a lot of people from all over the world on site. You know? I mean, it was really challenging for me. I mean, just still learning proper English just to try to communicate with people and everything. But at the beginning was quite challenging. I mean, just hearing, trying to understand, I don't know, people from US, but come from Texas and some other from the UK, and people from Japan trying to speak English. Come on, I mean, it was really tough and challenging, and but you get used to it. And that was in the construction phase. There is a lot of people from all over the world on site to interact with. But nowadays, it's basically, let's say, I don't know, 85 or almost 90% of the people is just local stuff. And just few people, that's mainly astronomers and fellows and few managers that still out of the Chile, that there's already speak Chilean. But yeah, I mean, that was the difference between the different stages of the array. But it was quite interesting and rich, I mean, opportunity just to work with all of them.
Nice. Okay, cool. Very cool. And then I guess I have one more final question. It's about as much time as we have. I'm personally curious how much into astronomy you were before you started working at ALMA. And was this the intention with starting to work at ALMA, or have you gotten very into it since, or is it just,
I would say,
an engineering job, you know?
Yeah, I would say the only related astronomy before came here, it was just that I love to do astrophotography, and that was the only thing before that. But of course, when the opportunity just to be part of ALMA arises, okay, I just bring my camera here and just enjoy that part of it and learn quite a lot from the astronomers and scientists about the constellations and how the the Milky Way looks like, and in the southern hemisphere, that was looking from some of the slides that were presented by Kristina, that it was really fun because totally upside down what we're looking here. So, but yeah, that was my previous relation with astronomy before came to ALMA.
Awesome, very cool. Yeah, I'm hoping to be able to get to the southern hemisphere at some point. I haven't been able to yet. I was a theorist, and so I never used the ALMA telescopes, unfortunately, to travel to Chile. But thank you so much, Pablo. That was an amazing talk. And there's a chance Pablo might be hanging around in the chat to answer questions if people have them. But if not, Kristina has linked Pablo's Instagram with some of his pictures and things like that that you can check out to reach out to him. So thank you so much.
Absolutely. It was a pleasure. Thank you.
All right, and so now we are going to be hopping to finishing up our trivia. And so you go back to the, let me see this. So if you go back to our trivia form that maybe Catherine can link again. All right, awesome, thank you, Catherine. And we'll finish up the trivia, the final 5 questions of the night. And so question number 6 is just like we go around the sun once a year, the sun goes around the Milky Way. Question is, how long does it take to complete a Milky Way year for our solar system? Is it 230 million years, 230,000 years, 230 years, 230 days? Whoa, there it goes. If it was 230 days, we'd be flying pretty quick. Or 230 seconds, we be zooming. So yeah, so how long does it take to complete one Milky Way year? Question number 7. Summer can bring extreme heat, but even more extreme is the hypothesized heat death of the universe. What is the heat death of the universe? Is it that the universe collapses onto itself like a black hole? The universe rips apart? The universe becomes inactive and freezes? The universe becomes hyperactive and combusts? Or the universe forgets to turn on the AC? Question number 8. A planet can get hot, even outside of the summer. Which of the following does not have a significant impact on the surface temperature of a planet? Is it the composition of its atmosphere? And this is which does not have a significant impact on the surface temperature of the planet. The composition of its atmosphere, the temperature of the planet's star, the reflectivity of the planet's surface, so how much light does it reflect on its surface, the number of moons it has, or the planet-star distance, how far away the planet is from its star. Question number 9, when we think of summer, we usually think of more daylight. Depending on your latitude, the time the sun is above the horizon or the length of a day can change. But what about on the moon? How long is a lunar day? Is it a half an Earth day, 1 Earth day, 14 Earth days, infinite Earth days, or every day is a good day on the moon? And then question number 10, even outside of summer, the Earth is getting hotter. This is due to the greenhouse effect caused by the emission of CO2 or carbon dioxide, along with some other gases. Which solar system object has an even stronger greenhouse effect in its atmosphere? Is it Mercury, Venus, Mars, the moon, or Pluto? And so that is going to wrap up our trivia for tonight. Make sure to get that in before the start of our final talk of the night. Submit that before the talk. So that's about 8:30. You'll have 15 minutes, 20 minutes or so to fill that out. You can do it along with some of the other segments that are going on. But for now, what we're going to be doing is jumping into Dr. Ed Murphy's segment, where we're going to be combining what's up in the sky with astronomy in the news. And so go ahead and take it away, Ed.
Thanks, Matt. Thank you so much. So what's going on in the news today? Today, of course, is the first full day of summer here in the Northern Hemisphere. And for Pablo down in Chile, it is the first full day of winter down there. And so I thought I would talk a little bit, since it's in the news, about our seasons for a second. And the first thing I want to mention is that, of course, our distance to the sun has nothing at all to do with our seasons. It's a really common misconception that somehow our seasons are related to our distance from the sun. So the Earth is in a very slightly elliptical orbit around the sun. But the Earth's orbit is so close to a perfect circle that if you didn't know it was elliptical, you couldn't tell just from looking at it. When the Earth is closest to the sun, we're about 147 million kilometers away. And when we're farthest from the sun, we're about 152 million kilometers away. And you might think, well, that's 5 million kilometers. That makes a lot of distance. But it's important to remember that when we are closest to the sun, we're about 1.7% closer than average. And when we're farthest from the sun, we're about 1.7% farther than average. And 1.7% in a change in distance to the sun really isn't enough to explain the difference between a really hot summer day and a really cold winter day. Let me give you an example. Imagine that you're standing around a campfire and you hold your hands up to warm your hands at the campfire. And you're standing about 15.2 feet away from the campfire. As you can imagine, going from 15.2 feet away from the campfire to 14.7 feet away from the campfire isn't really going to change the amount of heat that you get from the campfire very much. It certainly won't explain the difference between a cold winter day and a hot summer day. Our seasons are actually caused by the tilt of the Earth. The Earth orbits the sun and it's tilted over by 23.5 degrees. Now, this tilt remains constant as the Earth orbits around the sun. The North Pole axis of the Earth always points to the North Star Polaris. And as the Earth goes around the sun, the North Pole always points in that same direction. One of the other common misconceptions about the seasons is that the tilt of the Earth is changing during the year. And I want to make it clear that the tilt stays constant at 23.5 degrees. What happens over the course of a year is that as the Earth orbits around the sun and that axis remains steady, different hemispheres are exposed to the sun in different ways. In June, the Northern Hemisphere has its maximum exposure to the sun, and in December, the Southern Hemisphere does. If we take the Earth's equator and extend the Earth's equator out into space, you can see that the sun is sometimes south of the equator, crosses the equator, it's north of the equator, crosses the equator, it's south of the equator, crosses the equator, and it's north of the equator. And during the course of the year, the sun is going from below our equator to above our equator to below the equator, not because the sun is doing anything, but because the Earth is orbiting the sun when it's tilted over. So what effect does this have here on Earth? Well, it has the effect that most people are familiar with, is that it changes the length of our day. I think it's fascinating that everybody knows that the days are longer in the summer and the days are shorter in the winter, but most people probably can't give a good reason for why that is. Why are the days longer in the summer and why are the days shorter in the wintertime? And the answer to that has to do with where the sun is located. When the sun is on the equator, and that happens on 2 days of the year, March 21st and September 21st, we call them the equinoxes. The sun spends exactly half a day above the horizon and exactly half a day below the horizon. It's up for 12 hours, it's down for 12 hours, and that's where equinox comes from. Equinox means equal night, day and night are equal in length. But when the sun is north of the equator, as it is on June 21st, when it is at the furthest north of the equator, the sun rises in the northeast, makes this huge path across the sky, sets over here in the northwest, and it's up for a lot longer than 12 hours. And you can even see that from this diagram. Look at how long the sun is in the sky here, and look at how short it's in the sky below the horizon. In December, the sun is 23.5 degrees south of the equator, and it rises in the southeast and it sets in the southwest, and it makes this little tiny arc in the sky. It spends most of its time below the horizon. Here in Charlottesville during the summertime, we get about 14.5 hours of daylight, and we only get about 9 hours of night down here. In the wintertime, we get about 9 hours of day and almost 15 hours of night. So the length of the day has to do with the fact that the sun is north or south of the equator. A beautiful photograph that shows this was taken by an astrophotographer in Turkey at a latitude that's pretty similar to our latitude here in Charlottesville. And it shows the path of the sun on 3 of these marker days of the year. The top one up here is the summer solstice. This one is the equinoxes, and the bottom one is the winter solstice. And what you'll notice is that each of the suns is an hour apart. And so if you count the number of suns, there's sunrise 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hours. At that latitude, the sun is up for 16 hours in the summertime when it's north of the equator, and it's only up for 1, 2, 3, 4, 5, 6, 7, 8 hours in the wintertime. The other important thing to understand about our seasons is that how high the sun is in the sky determines how well the sun does at heating the surface of the Earth. When the sun is high overhead, it's much more effective at heating the surface than when it's low in the sky. So our seasons are caused by 2 things. They're caused by how high up the sun is, which is the more important cause. And it's also the fact that our days are longer in the summer and shorter in the winter. So what happened yesterday? Yesterday was June 21st, and yesterday was the summer solstice, which meant the sun is farthest north of the equator for the year. So those of us in the northern hemisphere have our longest day of the year. Those Pablo in the southern hemisphere had his shortest day of the year down there. For us in the northern hemisphere, we mark it as the first day of summer, and in the southern hemisphere, they mark it as the first day of winter. Also coming up, surprisingly, related to our seasons, is the fact that we will be farthest from the sun coming up in just a couple weeks in July. And I said that correctly. We are actually farthest from the sun in July, and we are closest to the sun in January. Just more proof that our distance from the sun has nothing at all to do with our seasons. I also wanted to point out very quickly some of the things that are going to be up in the sky this summer. In terms of planets right now, we don't have many that are visible in the evening sky. We've got brilliant Venus and dim Mars that are just in the west-northwest about 45 minutes or so after sunset. Venus will be putting on a show for the rest of the summer and through the fall, October and November, but unfortunately it's never going to get very high. Although Venus will be bright, it'll be down in the treetops down here all end of summer and early fall. Mars is rapidly disappearing and is going out of view. Venus, as you probably heard, is going to be visited by NASA at the end of this decade. NASA announced 2 new missions that are going to Venus. One of them, called Da Vinci, will actually have an orbiter in orbit around Venus and a spacecraft that's going to parachute down through the atmosphere of Venus and measure the composition of Venus's atmosphere. The other one, called Veritas, is actually going to use a radar mapper to map the surface of Venus. So for the first time in a long time, the United States is going back to Venus. We haven't gone back to Venus since the Magellan mission in the 1990s. The European Space Agency is also building a new mission to Venus called Envision, which should also arrive in the early 2030s. And later this summer, you have the opportunity to see both Jupiter and Saturn. They will be at opposition. Opposition is when a planet is opposite the sun in the sky. That's when the planet is both closest to Earth and appears largest in the sky, and is up around midnight. And so Jupiter will be at opposition around August 19th, and Saturn will be at opposition around August 2nd. Now, just because they're at exactly opposition on the 19th and August 2nd doesn't mean that you have to observe them on exactly that night. Because Jupiter and Saturn are so much farther from the sun than we are, they're actually really good for about a month or two before opposition and about a month or two after opposition. So starting in late July through August and September would be a great time to get a telescope out and take a look at Jupiter and Saturn up there. And lastly, in terms of the constellations that are visible this time of the year, we've got Hercules up there in the sky, the hero. Draco the dragon is visible high overhead right now around 10:30 in the evening. And then the summer triangle, the beautiful summer triangle, is bright and rising up in the sky. And the summer triangle will be high overhead all summer long. And it's made up of 3 bright stars, Vega, which is in Lyra the harp, Deneb, which is in Cygnus the swan, and Altair, which is in Aquila the eagle, one of the most easily identifiable asterisms or interesting shapes in the sky that's easy to find with these 3 bright stars high overhead all summer long. So I think I'm out of time, Matt, so that's all I have. I'm happy to take any questions.
All right, sure. Yeah, thanks so much, Ed. We do have a couple of questions actually for you. If anyone else has a question for Ed, feel free to ask in the chat. I mean, we have a couple of minutes, but Marilyn was actually asking if you could talk a bit about 24 UN 271, if you know what that is, and why astronomers are excited about its arrival near Saturn in 2031. So actually, I'm not quite sure what this is, but maybe you do.
So if I remember correctly, this is essentially a Kuiper belt object, although it wanders quite far in from the Kuiper belt. So it's an object that orbits in the distant solar system, and it will have its perihelion, its point closest to the sun in 2031. So, you know, I'm not sure that astronomers are as excited about it as the media. We study these kinds of objects all the time. When it's closest to Saturn, when it will be at its warmest, if it's made primarily of ice, there may be some indication of this thing shedding an atmosphere like Pluto does, but I don't study these cold icy bodies, so we'd have to ask one of our other scientists, Ann Verbisher, about that.
Okay, great, thanks. And then one more question. Eric Anderson was wondering, we now have 2 occupied space stations, the International Space Station and Tianhe. What is known about the plans for the Chinese space station? Is it intended for long-term use?
Yeah, excellent question. So for those that aren't familiar, China launched the first main component of their space station a little more than a month ago. And then just a few weeks ago, they launched the first 3 astronauts up to Tianhe. So right now there are 10 people living and working in space, 7 aboard the International Space Station and 3 aboard this Chinese space station. This is intended to be a permanent space station, or at least a long duration space station. China has previously launched 2 space stations, Tiangong 1 and 2, and they were short-lived. They were occupied. They had a few missions to each one where the astronauts would go up, live on board for a few weeks, and then come back home. And then both of those space stations ended up being deorbited. The goal for Tianhe is to keep it up for a very long period of time. Next year, they will be launching 2 additional modules to it. So they're building it as we built the International Space Station in a modular format where they launch a main module first, and then they launch subsequent modules later and attach them to it. So this is a long-term space station for China. And initially, they're just going to have short stays on the space station. But as they build up experience and capability, I think a long-term plan is to have it permanently crewed, to have a crew on board at all times. But that won't happen initially.
Very cool. Okay. Nice. Awesome. Well, thank you so much, Ed. If anybody has any additional questions for Ed about anything in the night sky or astronomy in the news, feel free to ask them in the chat. But other than that, thanks again for an awesome segment, Ed.
Oh, thanks, Matt.
All right. And so now I'm going to give everyone a 1-minute warning to go ahead and submit your trivia answers because we are at the final talk of the night. Oh, Bri, it was okay to keep sharing your screen if you want it. And so our final talk is going to be by Bri Mills. Bri is a graduate student at UVA, and she studies black holes and what she calls their donuts using computer simulations and real telescope data. But additionally, Bri is also interested in combating climate change. And she mentions, as Carl Sagan says, there is no planet B. So why don't you go ahead and talk to us about the cosmic donut makers, Bri.
Great, thanks so much, Matt. I'm excited to talk to you all about black holes today. Wish I could talk about climate change too and all the other things I'm interested in, but today will be black holes and the donuts that they make. So let's get into it. All right, so first I want to start off with a question for everyone, and that is, how many stars do you think there are in our Milky Way galaxy? Just the Milky Way. You can go ahead and put it in the chat if you want. I think we know it's at least one, right? We know our stars in the galaxy, I hope. Oh, I see some 105 billion, thousand, million. I think it's billion, yeah. 1 million, lots and lots. Yes, yes, all great answers. It turns out that the number of stars in our Milky Way galaxy is about 100 billion stars. So Matt wasn't too far off from that. This is a lot of stars. That's a 1 with 11 zeros after it. So a lot of stars. One less than Matt's. Great. So with billions of stars, and this is just in our Milky Way galaxy. This isn't including all of the billions of other galaxies that are in our observable universe, right? So just in our Milky Way galaxy, there's 100 billion stars. So that means we have lots of stars of different sizes and different masses. So to give you an idea, here is a reference for our sun, right? This is the size of our sun. There are stars that are smaller than our sun, like Proxima Centauri here. This star is our closest neighbor. It's about 4 light years away, which means that light, the fastest thing we know of in the universe, would take 4 years to get from Proxima Centauri to us. So I don't think I could outrun that in any way. So that's the closest star to us, and it's pretty small. There are also massive stars, way bigger than our sun, and they can get up to hundreds of times the size of our sun. So these are the stars that I want to focus on in particular for black holes, because these massive stars, when they die, they will give birth to black holes. And I'll talk more about that in a second. But before we get into black holes, I wanted to first talk about gravity, not just the force of gravity, but gravity as Einstein knew it. So Einstein, a candid picture here of Einstein, he believed that gravity was more like curved space, right? So if you imagine a trampoline, right, and you put a bowling ball at the center of that trampoline, the trampoline is going to curve underneath the weight of that bowling ball, right? So the same thing happens in space. So our sun, being so massive, is going to curve space in the same way. There's going to be curve under it, right? This also explains the curvature or the orbits of the Earth around the sun and all the other planets, right? So if you imagine taking a tennis ball and rolling it on that same trampoline with the bowling ball, what happens to the tennis ball? It first goes straight, but then it's going to feel the curve of that trampoline and spiral around the bowling ball in orbit around. Right, so that's exactly what our planets are doing because of this curved space-time or this curved trampoline. The key takeaway here is that the more mass you have, the more curve you're going to get, right? More mass, more curve. That's the thing to remember when we talk about black holes. Okay, which is now, we're going to talk about black holes now. So the question you all might want to know is, what are black holes? And Kristina talked about this a little bit in her talk with supermassive black holes, right? These are really dense regions in space. They have a massive amount of gravity. And as I mentioned earlier, they're just collapsed stars, right? These are massive stars that have died and collapsed down into a black hole, right? So to understand black holes, we have to understand the collapse of stars or the death of stars, right? So not to be confused with the Death Star. We're not going to talk about the Death Star. We're going to talk about the death of a star. Though I like the Death Star too. So what happens when a massive star dies? Well, stars are just balls of gas, right? They're fusing hydrogen into helium at the core of the star. That is the definition of a star, fusing hydrogen into helium. So what happens when that helium runs out? Well, the star will start to collapse down because gravity is now taking over. But then the star is going to realize, oh, wait, I have helium left, right? So I can take that helium and I can make carbon, nitrogen, oxygen, all the way up to iron. And when it does that, when it's fusing helium now, it becomes a red supergiant. It'll puff up and it's fusing all of that into carbon, nitrogen, oxygen. And then what happens when it runs out of helium? Well, it'll collapse down again, but this time it's going to collapse so fast that it's actually going to explode and it's going to go supernova. So these supernova are amazingly violent things that happen. These explosions are very, very violent, but also very beautiful. So you can Google some pictures of supernova later. There are some really, really beautiful pictures of supernova. And this is where the phrase, we're all just stardust comes from, right? So we are made of carbon, nitrogen, oxygen, iron, phosphorus, all of that's in us. All of those things they came from stars. So all the stuff we're made of was once made in a star that then went supernova and blew all of those elements out into the universe and into our galaxy. So what does this have to do with black holes, right? So when a star goes supernova, what's left at the center, depending on how much mass there's left collapsing, will either be a neutron star or a black hole, right? We'll just focus on the black hole for now. If you have a lot of mass and it keeps collapsing and collapsing and collapsing, it'll collapse all the way down into a single point, right? So what does that mean? What does that mean to collapse all the way down into a single point? So I'm going to show a little animation. Remember the trampoline, again, representing space-time. And if you have more mass, you're going to have more curve. So let's put a massive star at the center of that trampoline and collapse that star down to a single point. And watch what happens to the space-time when that happens. You're going to create a hole in space-time, or black hole. So the black hole is now a singular point all the way in the middle there. And you'll notice this very dark region in the center where you can't see anything. That we're going to call the point of no return. Anything that goes into this hole cannot escape. Not even light, the fastest thing in the universe, cannot escape the pull of a black hole. It is that just crazy, right? But anything around the black hole, if you don't go past that point of no return, if you just kind of skate on by, you'll just orbit around, right? So that's the circle of swirling stuff you're seeing, stuff that hasn't gone through the point of no return yet. Okay. So if you've ever Googled a picture of a black hole, you might have seen something like this. And if you've seen the movie Interstellar, which I highly recommend you go watch the movie Interstellar, you would recognize this picture of a black hole, which they named Gargantua. Fun fact, Interstellar's director, Christopher Nolan, he actually worked with a physicist. His name is Kip Thorne. They both worked together to create this image of a black hole, the most realistic looking black hole in Hollywood, and probably any movie. I've never seen a really good depiction of a black hole, and which was really crazy because, you know, most sci-fi films and stuff, they don't have physics or science at the forefront of their mind, right? What do they have at the forefront of their mind? It's money. They need to make the biggest bang or make the flashiest thing. So the fact that they pretty much got a black hole almost right, they were missing a couple things, but we won't talk about that. It was pretty amazing to see that. And this is what we thought black holes looked like up until the Event Horizon Telescope was able to image a black hole for the first time. So this is a real image of a black hole, a supermassive black hole, just like the ones Kristina was talking about. This one is about 6.5 billion times the mass of our sun. Huge. This is the real Gargantua, honestly. So this supermassive black hole is at the center of a galaxy called M87, and which is about 55 million light years away. So the light that came from this black hole had to travel 55 million years just to get to our telescope, which is crazy. Like we're all time travelers right now looking at this picture, right? So you are looking at this supermassive black hole as it was 55 million years ago. How incredible is that? Right? Even though it's blurry, it's still fantastic for a black hole picture. Okay, so I said that this picture is of a black hole, but that's a little misleading. We're not actually looking at the black hole, right? Because you can't see anything inside the point of no return. No light is coming out, so how can we see anything, right? So what we're actually seeing is the donut around the black hole. That's this ring here. And the black hole is in the very center there, in the very point where the trampoline is bending down underneath the mass of that black hole. Crazy, right? And these donuts, for the longest time, I call them curlers. They're crullers or crullers. Yeah, drop your favorite donut in the chat too while you're at it. Yeah, so we see donuts around black holes, and that's how we observe them. Kristina actually hinted at this earlier too, where you see X-rays coming from black holes or radios, light coming from black holes. We see these donuts giving off that kind of light, and that's how we know that there's black holes there. Also, seeing the orbits of stars around black holes, you can also infer something massive must be there. Right. All right, so let's take a closer look at what these donuts might look like around a black hole. So we're going to zoom in into a galaxy. You see the jets Kristina was talking about earlier too. So this is a swirling hot mess of gas. This is hot gas swirling around a black hole. This is what we're calling the donut. So much stuff is going on here. It is very, very hot. There's a lot of collisions going on, a lot of friction, heating up everything around. Notice what the particles do, the light particles do at the very center. They are getting slingshotted by the black hole as they get close. They either go into the black hole past the point of no return and disappear, or they get slingshotted. So all those light particles that get slingshotted to us is what we see. That's the donut of slingshotted particles to us. Great. And you can see that point of no return there. This is the point of no return. That's that dark circle in the middle. Really, really cool. So where does the black hole get its donut ingredients? I said it's hot gas, but where is it coming from? So it can come from a couple of different places. For example, if there's a nearby star, if it had a little companion star, it can strip gas from that star, because stars are balls of gas, right? They're perfect ingredient sources. Hopefully it's being sustainably sourced. So they can strip gas from stars. Or for supermassive black holes in the centers of galaxies, they can get gas and dust from within the galaxy. And if there's orbiting stars around it, if that star comes a little too close, it'll just take and take and take gas from it and feed itself. Right. I also mentioned that it's really, really hot. So how hot is it actually? How hot is that donut around the black hole? Well, first, think about the temperature of oil to fry donuts, right? It's probably a reasonable temperature. It's about 375 degrees Fahrenheit. Still a little too hot for my liking, but hot enough to fry your donuts. What about the temperature of a black hole's donut? Well, it's about 17,999,540 degrees Fahrenheit. That is hot. That is too hot. That means the hot sign is always on for these black hole donuts, always on. Usually that's a good sign. You want to see that hot sign so you can go get some hot donuts. Not this one. Do not recommend you eat this donut. Please don't. I'm not liable for any person who eats donuts around black holes. Just putting that out there. All right. And so I want to come to my last point, and that is, if we're going to call this a donut around the black hole, this hot gas, a donut, doesn't that make the black hole a donut hole, right? Black holes are donut holes. I'll take my Nobel Prize. And with that, I'll just end on a sweet note and just summarize all the things that I pointed out here in this presentation. If there's any Nobel Prize people in the audience, please contact me about this black hole equals donut holes thing. My email is bri@virginia.edu. I'd love to have a Nobel Prize. And we also learned that gravity plays a really important role in the collapsing of stars, forming black holes, but also the black hole's gravity itself brings the donut together and makes it circle around. And that donut is really, really hot. So with that, I'll take any questions, put them in the Q&A. Thank you.
Awesome. Thanks so much, Bri. I never thought that I would want to eat donuts so much after an astronomy talk, but here we are. We're going to have to do an astronomy on donuts at some point, I feel like, based off of that. But yeah, we do have questions in the Q&A. People are still able to ask some as well. But Daniel, hello, by the way, she is asking, when we look at black holes with the Event Horizons Telescope, we are able to see light from background sources due to gravitational lensing, or is it just material from the accretion disk?
Oh, I want to say both. I mean, this picture behind me, that's like what you're talking about, the gravitational lensing, like the light that's on top of the black hole and below, that's actually behind the black hole. So the stuff, the donut gets lensed, but black holes are so massive, they can also lens things behind them too. So yes, both, I think.
Oh, very cool. All right, so then I also had a question. I was curious if you mentioned, so that the intense energies and temperatures around black holes, right? So if we imagined we were like in the year 4000, speaking of energy and using reliable energy, is there a way we can take advantage of the energy from black holes or anything interesting regarding that? Just out of curiosity.
Man, that would
Or is that
be
a super
incredible.
challenging question? I'm sorry if it is.
I think, I want to say Interstellar kind of got at that too, where they were like harnessing the power of black holes and time and stuff. And I still don't understand Interstellar, but yeah,
Okay.
I would love to say, yeah, I mean, these are pretty powerful sources. Kristina was also hinting at that earlier, like launching powerful jets and stuff. Yeah, I don't know how they would do it, but I'd say, yeah,
Yeah,
that'd be cool.
I've always heard that like black hole might produce energy that's potentially more efficient than like fusion even. So that's why I was like, curiosity piqued that. Okay, cool. And then also, so we're talking about supermassive black holes. You said black holes formed out of just collapsing stars. The ultimate question though involves, how do supermassive black holes form? So I was wondering if you could talk a bit more about that, or if I had missed that, I apologize that if you had mentioned that in the talk.
Yeah. So supermassive black holes, I think there's so when the universe was formed, they think that there's black holes that were formed then, and those were probably the most supermassive, massive black holes. The collapsing star one, those usually form like solar or stellar mass black holes and stuff, depending on the mass of the star that was left over. But right now, we don't believe that black holes can grow into supermassive black holes, or at least there's no evidence for it yet. We haven't seen this like intermediate region between like a couple suns worth of black holes and like billions of suns worth of black holes. There's like nothing in between. So it doesn't seem like they're growing into supermassive black holes. They must have been born probably back when the universe was first beginning.
Very cool. Okay, cool. And then maybe we got one more question, unless someone else throws something in the chat very quickly. It's from David, wondering if there's such a temperature as a maximum possible temperature. I don't know if you know the answer to that, or if it has involves black holes as well, but maybe maximum temperatures would appear near black holes if that was the case. So
yeah,
maybe the
I'm not
temperature
sure
near black holes might have some guess about that. Yeah.
Mm-hmm. Yeah, if anybody else knows, you can throw it in. I think I haven't come across like a maximum temperature. I've seen like temperatures around the same range of like, you know, the billions of degrees Fahrenheit. That's kind of typical for a disk, or for a donut. But we have seen really, really high temperatures that looks like these donuts have atmospheres, like I guess like floating icing or something, where they're like really, really hot. It's like plasma icing or something. Yeah.
Oh, wow.
And that's like really hot. That's, I think, 10 times hotter, 10 times hotter than the disk itself.
Wow. Very cool. Black holes are crazy.
Yeah.
All right, so cool. So thank you so much, Bri. That was an awesome talk. If anybody has any more questions for Bri, you're welcome to reach out to her to give her a Nobel Prize, right? And then also to ask her any questions. So thank you. And we will end up wrapping up the night then by talking about the trivia. And so let me go ahead and start sharing my screen again. The sun is starting to set, so it looks like I'm getting a little dark in my lighting, but that's all right. Hopefully you guys can still see me okay. And so I wanted to remind everyone, we're raising money for the McCormick Observatory. If you're able to donate, we're still accepting donations, and all donations are being matched up to $250 by two really generous donors. So thank you so much for those of you that are able to donate. We appreciate any of those. McCormick Observatory would appreciate any of those for sure. Let's go ahead and go through the trivia answers before we reveal who the winner was. And so question number 1 was about summer being officially here, and which of the following is not true for summer in the Northern Hemisphere. And that is that the length of daytime starts getting longer. That is not true for summer in the Northern Hemisphere. Question number 2, our orbit around the sun is not a perfect circle. The point we are closest to the sun is called perihelion. What is the furthest point? When does the furthest point, or aphelion, occur? That is in early July is when we are farthest away from the sun. Even though that is when, as Ed had mentioned, the Earth is generally hottest at that point. It doesn't have to do with distance. It has to do with the axial tilt of the Earth. This was our Facebook trivia hint question. Summer lasts about a quarter of our trip around the sun. If summer were the same on Jupiter, so Jupiter doesn't experience seasons because it doesn't have an axial tilt. But if it did, how many months would it last? And the answer is 36 months. Additionally, question number 4, it's summer. Oh, and sorry, I should go back on that. That's because the length of a year on Jupiter is 12 years. So a quarter of Jupiter's travel around the sun, it would be 36 months. It's summer, it's hot, but it could be a lot hotter. What is the hottest planet in the solar system by average surface temperature? And that is the planet Venus. Venus has this runaway greenhouse effect, which causes its temperature to get on the orders of, I believe, 900 degrees Fahrenheit or so on its surface. We get more direct sunshine in the summer, and that's what helps increase the temperature. But the sun isn't the hottest type of stellar object. Which type below is the hottest? And that would be a white dwarf. A white dwarf is probably, is what our sun is eventually going to turn into over time. That is the hottest of these objects right here. And unfortunately, a giant volcano star isn't a thing. This is just a trick trivia question, as usual. Question number 6, just like we go around the sun once a year, the sun goes around the Milky Way. How long does it take to complete a Milky Way year for the solar system? It's actually 230 million years for the sun to orbit the Milky Way just once. So since the sun's formation about 5 billion years ago, that means that, let me do the math real quick. The sun is about 20-ish years old, I believe. Maybe some astronomers in the chat can correct me on that. The sun is about 20 years old in regards to the Milky Way galaxy itself. Question number 7, summer can bring extreme heat, but even more extreme is the hypothesized heat death of the universe, which I like to call the death of heat of the universe rather than the heat death of the universe. And that is because this is when the universe becomes inactive and freezes. It is the death of heat in the universe. A planet can get hot even outside of the summer. Which of the following does not have a significant impact on the surface temperature of a planet? That would be the number of moons. Moons can somewhat impact some things on the surface, but it doesn't have really as strong of an impact on the surface temperature of a planet. Question number 9, when we think of summer, we usually think of more daylight. Depending on your latitude, the time the sun is above the horizon or the length of a day can change. But what about on the moon? How long is a lunar day? That is about 14 Earth days for daylight to reach various surface on the moon. And then finally, question number 10, even outside of summer, the Earth is getting hotter. And this is due to the greenhouse effect, which I had mentioned on the planet Venus. And so which solar system object has an even stronger greenhouse effect in its atmosphere? That is the planet Venus. And so our trivia winners for today got 9 out of 10 questions correct. And so nobody got a perfect score, but our winners did get 9 out of 10 questions correct. And our trivia winners are as follows: Mike Napper, Ryan Thompson, and someone that just put their contact information. And so we are going to be reaching out to you guys to be able to send some Charlottesville Astronomy on Tap gear to you. And we're also going to be choosing some random winners to send some stuff to as well, to thank all of you guys for tuning into our virtual events over the years, or over the past year. And so finally, I want to wrap up by asking you guys for feedback. There's a chance we might be going to in-person events moving forward, but if we continue virtual events or if we go to in-person events, we would like any feedback that you'd be able to provide. And so I mentioned feedback. We talked about feedback. Kristina talked about astronomical feedback and its importance in active galactic nuclei in these jets that impact the evolution of the universe. But feedback helps impact the evolution of Astronomy on Tap Charlottesville as well. And so if you have any feedback, please click the link that Catherine just linked to help us make Astronomy on Tap Charlottesville better for everyone and the AOTCville community and family going forward. And so finally, I want to thank everyone again. Special thanks to the speakers, Kristina, Pablo, and Bri, Ed for doing the Astronomy in the News segment, some of the other volunteers, Molly, Jacob, Katerina on Twitter, then of course the organizers, Catherine, Brett, Marilyn, Whitney, and Scott. Regardless of if I'm in Charlottesville next year, this will not be the last time that I see the Astronomy on Tap Charlottesville community. There's a chance you might still be seeing my face 2 months from now anyway. But of course, thank you to all of you guys for the fun over the past 1.5 years as I've been leading Astronomy on Tap Charlottesville. And I hope I can stick around in Charlottesville to have some more Astronomy on Tap fun with all of you guys. So for now, thank you all to everyone tuning in, and I hope to see you guys some other time. So Buzz Lightyear signing off. Thanks, everybody.